topic, lithium battery. Why do we want to research lithium battery? Let's first scare everybody a little bit. If we do not do that, the ocean will rise and we're all going to have neighbor with a fish. And this is going to happen in 2012. Of course that didn't happen, but it's going to happen. Unless everybody drives electrical cars. So that's the motivation behind why do we need to study battery research, because a battery is basically everywhere, and using new technology, new energy will actually help us to make the air more clean and many different things. Lithium battery is a very high performance, small volume, very lightweight of technology. We all wear one of these in our phones, and it has a lot of advantages over different kind of battery technology, and that's why we focus on the lithium battery. There's a lot of research using microscope technologies, and let me see if this is working. And we see a lot of works using SEM, and a lot of works in the AFM, and so on and so forth, and that's not my expertise. And one thing I wanted to mention by looking at the various different research using SEM and AFM is that a lot of work that we study the surface layer of the electrode of this battery are based on ex situ. What ex situ means that you finish your discharge, and you cut open your cell, you take out the electrode, and then you put it in the microscope and you observe them. It's ex situ. What does it mean? That whatever the things that you put on there, it's already dead, it's already frozen, ex situ. And it's not as, to my opinion, as exciting compared to in situ. The reason we choose AFM and STM to do this type of work is that it has unique capabilities, and one of the things, it's very high resolution. This is STM I mentioned, and these images are taken in copper sulfate solution as we charge the surface and then form a single layer of a copper on the surface of gold, and then you observe it when the reaction is happening as it happens. So first thing is in situ, high resolution, and second is in situ. You observe it. There's some more interesting question. Here's another. It's just the electroplating of a copper on the surface of gold, and you can see the things happening as it happened in real time. Here's another. This is a combination of 100 images of a very simple experiment of a piece of calcite that is exposed to acidic water, so you can see the things dissolving as it dissolves. So this is a very unique for atomic force microscope compared to the other high resolution like SEM, TEM, is that you can see things happen as it happens. Now, next of course you need to combine the AFM STM with another piece of equipment which is called a potentialstat. We control the potential of your working electrode, which is the electrode you want to study, and you're going to have a counter electrode, you're going to have a reference electrode. So you need to have a potentialstat to control these electrodes. So you combine these two, you build AFM STM combined with electrochemical cell. This is a picture of the original manual of our AFM combined with the electrochemical cell, and these are basic essential components here. And later I'll tell you what's the problem with this design. So here is the electrode you want to study, which is this piece of either metal or graphite and so on and so forth. So that is the things you want to look at it. And second, you're going to have a counter electrode that form that allow the carriers, cations and anions to be absorbed here and then form a cell. And you're going to have a reference electrode which have very little current, and therefore you can measure the potential more precise. Well, one of the problems I can tell you is that lithium is a very active metal, and when you want to do lithium battery research, you go to this lithium battery research laboratory. One of the things you'd see immediately right in front of you is they always have arrays and arrays of glove boxes. The reason is that lithium is very afraid of oxygen and moisture, and you cannot handle them in air. That's one thing. Second is that you want to get rid of all the moistures and all this. So that's the first thing. And second is, you look at all these things, and this is how this electrochemistry cell is putting together. It's very good design, very small and very precise, everything is good. However, you look at all the little detailed things here. They're all very small, and later I'll tell you why this is a problem. Well, in order to get rid of the oxygen and moisture, and in order to have you to study the electrochemical cell using AFM STM, we actually had various designs of glove boxes. Basically, protects your sample and electrochemical cell from the moisture, from the oxygen outside. And these are a couple of different designs of glove boxes. And I actually used this glove box, did a lot of research. Now, there is still some fundamental problems here. The only problem is that the glove box is built with plexiglass. And we know plexiglass actually absorbs water. And therefore, it's very difficult for you to maintain a very high purity environment that there's no water there. There's always a little bit of water here. So that's another problem. It's a brilliant design. I actually worked in a workshop in a glove box company, and I sit with a worker, and we actually draw these things and build the whole thing together side by side. But there's some fundamental problems you cannot get over, basically the material itself. So ultimately, we tried two different ways of work, and this is one of the work that's done actually successful, not very easy, but successful, is we actually put entire AFM inside the glove box, because only then you can maintain the moisture level and oxygen level at very, very low level. That's the only way, because then the commercial or professional glove box, not only it actually isolates the atmosphere, it also has a catalyst to capture the oxygen and capture the moisture, to maintain the moisture and oxygen below 1 ppm. That's the only way. Now, that kind of solution introduced our next sets of problems. You look at that, you have to wear this thick glove to operate your instrument. So you have to adjust everything, you have to put all these tiny things together. And a lot of times the scientific research was actually become extremely difficult, and not because of some fundamental reasons. It's because of a lot of the practical reasons. Something's too small, too big, and you want to change something. And then the whole changing itself or redesign itself takes a lot of time. Or if the whole thing is difficult to put together, it takes more time. And then when every time you have 1% of success rate, and you have 10 different steps, they make your success rate very low. So the graduate student, why do we spend 5 years or 6 years in school, and the actual experiment only happens in a week, right? Because most of the time we fail because we're dealing with failures. Okay. So the things I show you, things all the scientists that we talk about, there are successes, and then when we write paper, there was something very interesting. When we write paper about AFM STM, we submit, and then the editor always sends the paper back, say, hey, remove all the word easy from your paper. Because it's not easy. It's easy that time. It's not easy at all. So sometimes we did something so difficult and we're so proud of ourselves. We put a lot of easy in our things. Use my method, use my technology, it's easy to this and that. It's not easy. Well, this is one of the ways to, even you put the instrument into a glove box is a gigantic work. It takes a lot of time. See, in this case, the entire front panel of the glove box is removed, and they put the instrument inside the box, close it, and whenever inside, it's inside, whenever outside, outside. You cannot touch it anymore, right? It's even you change a part, takes a minute. Here, you change a part, take a week. Not easy. So this is a solution. First, this whole thing is a vibration isolation. It's gigantic, it's heavy, and it's big, and you have to take the front panel. So I come up with a solution. So these are Thor lab frames, and this whole thing can be disassembled into pieces, and every piece will fit into the transfer chamber of that glove box, and therefore you go inside and you wear your glove and you assemble it. So the whole thing allows you to take care of the vibration problem of the AFM inside glove box. This is what it looks like. And this little rubber band, and I tried a different rubber. I tried about 10 different kinds of rubber band, and these rubber band, this particular color rubber band from Walmart, not Walmart, Maya worked because it allowed this whole thing to have about 1 hertz of oscillation, and then at that point you can actually It's a little more fancy here. You can actually achieve atomic lattice using AFM, and atomic resolution was STM, actually. That's a different look of it. So this is what this piece take apart, and then you can put together with these tools, and it's not easy because all these screws are very small. And then this is what it looked like inside glove box, and then again you cannot even put your head behind the instrument because you're right in front of it, and you wear two thick gloves and assemble this thing together. But this allows to have one ultimate test. This is a atomic lattice scanning on graphite, and that's okay. Now our noise level is okay with this vibration isolation. That problem is solved. Next problem I mentioned before is these little parts, right? So you look at them. Let me show you the manual. Okay, this is the screen capture of the manual of our AFM combined with the electrochemistry. It says you have to bend your electrodes into this shape, right? Anybody handled the lithium will tell me you cannot bend the lithium into this shape. Lithium is very soft. You handle lithium, you're like handling halfly cooked noodle. They're very soft. It does not have a shape, right? And plus, you really don't have hands because you have a thick gloves, you have tweezers. That's all you have. What are you going to do, right? So there's many different approaches. I was teaching a student for the entire year and to bend this, just to bend this, right? So your tool is not working. At that point, it was about 2 to 3 years ago, and I was probably very similar to everybody sitting here. I was a chemist 3 years ago. Later, I became a mechanical engineer because of these frustrations. I don't understand why it's funny. It did happen. All right, this is some designs. Okay, so this is a solution. I took a picture from Lawrence Berkeley, and they're brilliant in doing the research. They have a lot of papers, and I was saying, show me how do you do that? And they showed me this is. I look at it and see those little nuts. It's so small, and you drop it, you never find it. These are the hands that handle it. And then here, that's their way to dealing with corrosions. You take the whole thing down, deal with corrosions. So that's an average chemist or material science are facing every day, day in, day out, is that the experiment is very difficult. So at that point, I say I had enough. I don't want to be a chemist. Being a chemist, have a PhD in chemistry is a mistake. So I live in Detroit, and we have a lot of talented people, so I mixed up with a lot of workers, and I also worked with a lot of 3D printers, 3D printing and so on and so forth. And on Thursday, I'm going to tell you this 3D printing is useless, and why is that? I'll come back in Thursday. At that point, I did not know how to do mechanical engineering. So this piece, this is a square liquid cell. Why it's a square? Because you can grab it, simple. Right? And why this circular? And why this circular is this particular shape? Because I can find a drill bit this big and cut this. And why the graphite is glued there? There's many reasons, because I can show you a pile of failures and why it didn't work. So that's my liquid cell. Actually works very well because it's a square, and then if you don't like it, you throw it away. And this is a brilliant invention that I worked out with as a postdoc. See this little cage? It's difficult to bend your lithium into a shape. However, you can wrap a very soft noodle around a spindle. You can do that. That's not too hard. So this is actually a little spindle that they cut from the machine, and then there's little holes that can allow current to pass. So you wrap this thing around it and leave. See, this is lithium. Wrap around and cut and push into it, and then connect these two. So you change from bending wire into wrap something. That's much easier and much quick. Increase your success rate much better. So this is what this liquid cell looked like at that time of experiment, and I'm going to continue to show you the experiment I did. This is a cycle of a thermogram of this EC cell, and this is first cycle, second cycle, and third cycle. I'm not an electrochemist. If you ask me a question right now, I will not know the details, but this is the EC cycle of a thermogram we did on this particular cell. And this is what we see. This is the very first experiment we did. And you see a lot of noise here, because at that time I did not figure out the vibration isolation yet. So you have about a 1.5 angstrom noise. So here's what happened. We're charging the electrode, which is a graphite, at 3 to 2.95 volts. That's graphite surface. You have a little bit start to happen. At 1.7 to 1.65 volt, as you charge it, you started to form a little cluster here, and the graphite cells still have no change. and we believe something happened, and we believe it is the decomposition of lithium alkali carbonate from a polymer on the surface. C is on 1.0 to 0.95 volts and so on and so forth. At about 0.5 volts, this is something happened. From here to here, there's a lot of wild driftings in the system. We don't know what happened. Later on, we'll find out what happened. Is that here we see a formation of little clusters. And these clusters actually stick to the surface of the electrode. At a certain point, about 1 point some volts, right here, these formed this cluster. They form a crust. And this point, the crust actually leaves the surface. They delaminate it. That's what we saw. Because it delaminated, we could use AFM tip to remove the first layer and expose the second layer. See what happened. And we see that the second layer has also had some changes, but its changes is very different. See, this is let's see what it is. It's pristine HOPG, has some noise. And this is discharge at 1.7 volts. You can see there's a lot of steps started to increase thickness. All right, we know that atomic steps has a fixed thickness because it's the size of the interatomic distance of layers of graphite. And why increase distance? That's because the lithium ion actually inserted themselves between the two sheets of graphite. That's what we believe. And this is the model we come up with. This is actually come up with Dr. In of Wednesday University and collaborate on this. So at the beginning, we will have these decomposition of the lithium carbonate, the lithium alkaline carbonate on the surface. And as they form more, another process happened, which happened in the underlying surface. We do not know when it happened because it's covered. And that's called the insertion of the lithium ion. They actually solve it, insert themselves into the graphite and cause the graphite to curve. And at a certain point, cause the graphite layer to swell up and therefore cause the first top layer of SEI to delaminate. And this is another example of that. We actually zoom out. You can see that little things. Here is underlying, and there's a crust there, and then there's no obvious attachment between these two layers. As a matter of fact, in the real experiment, that it's very easy for the entire thing to come out, and if the force is too high. So actually, it's confirmation of there are actually two layers of SEI formation in this experiment. Now, we use a little bit more force and remove the first layer, and we'll look at the second layer. And look at the second layer. It has a very unique instinct look of it. It's very interesting. What does it remind you? Remind you of a bed sheet, a wrinkled bed sheet. And what the tells us is that maybe it's possible that the lithium not only inserted underneath the graphite, but also inserted in the crystal structure of graphite and cause it to swell, could expand laterally. That's what the wrinkled sheet tells us. And next thing we did, we apply a little bit high force and in this little square to see can we push it down. And that's what we did. We apply a little bit high force, about 10 nanonewtons, scan small size and scan large area again. We actually push them flat. So that's an evidence that these wrinkled sheets are actually not a solid material, but some soft material. Only apply force, you can actually squeeze out those lithium ion in the insertion in the graphite sheets. Some ongoing work, and naturally we're going to study the mechanical property of it using indentation. And this is the improved version of this whole liquid cell, and it looks much nicer. And the entire adapter is also made of Teflon. Every single part here can be bought cheaply. There's a $3 piece of things from Spark Fun, and these are some piece. And this is steel sheet, and the whole thing can be machined again. It's a lot of improvement, and this cage is also made much better. This design had a little cover that prevent evaporation. And this is another things that I tried. It is to build a heater inside the cell. Why we want to do that? Because the temperature actually affects your charging, discharging, affects your lifespan of your battery a lot. So we said we put a heater there. At this point, we did one test. After test, we realized the previous research that we did before, including all the research on the market, there's some information missing. What is the information missing? Let me tell you what's missing. Okay, there's a heater there, right? The first experiment we did with this is that we try to do that without heating. We run experiment before heating, right? Now, when we run 1 CV, the cell temperature shoot up to 65 degrees C. Now we realize all of our previous data has no temperature information. The temperature during a CV shoot out very high. So all the data we got is high temperature. So again, if you can put a heater, you can put a cooler, and there's a lot of more work you can do with this kind of thing. This is a design that we want to study. We want to feed oxygen underneath the porous sample, and so the combination of things is endless. You can keep pushing forward forever. And this is another thing I invented. I went to a couple of groups, and they studied the lithium battery research, and they want to study the lithium battery research. They want to take the electrode, unpack it, and they want to stick into SEM and study the surface, or XRD, or XPS, okay? Now there's a problem of doing that. When you open the package, the lithium is exposed to the air. So people are designing different kind of combination of connectors and protections and chambers and so on and so forth to try to open the package in the glove box, connect the glove box to a XPS or SEM, open it there so the sample never exposed to the air. I say, hey, don't use complicated solutions, because any complicated solution turn itself into a complicated problem and could ruin some graduate student's life. So I said, I'm going to think about it, and then this is what I dream of. It's very simple, because then you have a little cover here, and you have the sample holder, and you close the sample holder, and then there's a little latch here, right? And then you seal your sample in your glove box, and you put it in your SEM, and then you close the door, turn on your vacuum, and the whole thing pop out by itself. And
that really cool application note, we should end now and let that be for Thursday, because I think that's really relevant to a lot of people. Great. Well,
that's the video.
all right.
Anyway, Thursday we'll show you how to do these things. These are not difficult. You don't need $1 million 3D machine, 3D printing machines. You can do it. I did all of these in my own basement, with no help from anybody else. So that's why I turned myself into engineer. And please come to my next talk.
Great. Well, let's thank our speaker.